Hi everyone, and welcome to the second of 4 videos going through some past exam questions on the topic of intermolecular forces. In the previous video, we looked at a few questions that were mostly focused on one particular type of intermolecular force. We had some questions on London forces, and we had some questions on hydrogen bonds. The questions in this video are going to be comparing molecules with different types of intermolecular forces. So in this first question, it's asking us about HCl compared to F2. They've got the same number of electrons, okay, and yet they have very different boiling points. They're both low, right? Because all these types of intermolecular forces are weak. Intermolecular forces are weak in general, but the intermolecular forces in HCl must be significantly stronger than those in the F2, and that's why it has a much higher boiling point compared to the F2. So that's what we need to do. So we need to look at what type of intermolecular force they're going to be. Okay. HCl, now we need to be careful here because you might look at it and think, it's going to have hydrogen bonds, right? Because it's got hydrogen. But remember we said hydrogen bonds only occur between molecules where you've got fluorine, oxygen, or nitrogen. Okay. This is not going to be able to make hydrogen bonds. So it's just going to be a permanent dipole. Okay. There is still a significant difference in electronegativity, but it's not going to be classified as a hydrogen bond. Okay, so HCl has permanent dipole-dipole interactions. Whereas F2, there's not going to be a dipole, is there? Because it's fluorine bonding to fluorine. Okay, so they've got the same electronegativity, so it must just be London forces. So then we need to talk about explaining the difference between them. Okay, the permanent dipoles in HCl are stronger than the London forces in F2. So the intermolecular forces in HCl require more energy to overcome. We mentioned, didn't we, that that's usually a good phrase to put in any of these questions. And then this is why HCl has a higher boiling point. Okay. So we're definitely going to get 2 marks just for saying what type of intermolecular forces we've got. Then we want to do the comparison and then link it to the boiling point by saying it takes more energy to overcome. Moving on. We've got some data again given to us here. We've got different group 5 hydrides and their boiling points. And it wants us to say what intermolecular forces we've got. Okay, so whereas we said that HCl is not going to be able to have hydrogen bonds, if we've got nitrogen, we are going to be able to have hydrogen bonds. Okay, and we saw NH3 in the previous video, didn't we? We had to draw the hydrogen bonds. So this is certainly going to be hydrogen bonds. But then again, we've got the same thing here. pH3 is not going to make a hydrogen bond because you only have oxygen, fluorine, and nitrogen. But phosphorus is still reasonably electronegative, so it is going to have a permanent dipole. Permanent dipole-dipole interactions. And then why does it have a lower boiling point? Well, because the permanent dipoles are not as strong as the hydrogen bonds. Okay. So it's a very similar question to what we had up here, but they've just split it into different parts. Permanent dipole-dipole interactions in pH3 are weaker than the hydrogen bonds in NH3. And then just because we want to get into good habits, we want to then say, so they take less energy to break. Okay, we want to get that into as many answers as we can, just to be on the safe side. Right, the last question I want to look at in this video is a bit of a longer one. We've got 3 different molecules to look at here, and it's just saying, here's their boiling points, explain the different boiling points. Okay, so what's going on here? Include the names of any relevant forces and particles. Okay, so this is a bit, what do we mean by that? Well, particles, what the particles are going to be the molecules, aren't they? So this is just making sure that we've mentioned that they're intermolecular forces. So let's just list these, shall we? I think that's probably a good place to start. So NH3, let's get this in. So let's say the intermolecular forces in NH3 are hydrogen bonds. Whereas these two are both elements, right? So there's going to be no difference in electronegativity. These must both be London forces. Okay, let's just bullet point this. Okay, so this is good because that now means we've done this whole bit, right? We've included the names of all the forces and we've said the particles because we've said they're intermolecular forces. Okay, so now we just need to explain why there is this difference in boiling points. Okay, and before we go too much further, let's just have a look. So bromine has the highest boiling point, right? So this must have the strongest forces. And then fluorine has the lowest boiling point, so this must be the weakest, and NH3 must be medium. Okay. So is this what we would expect? Well, no, we'd normally expect the ammonia with its hydrogen bonds. We said hydrogen bonds are the strongest type of intermolecular force. We might expect it to have the highest boiling point, and yet it's lower than bromine. So this is a bit unusual, but we're going to have to go with, I mean, that's the data they've given us, right? It's not wrong. It must be the case that bromine's intermolecular forces are the strongest. Okay, so we can say bromine has the highest boiling point because its intermolecular forces are the strongest. And require more energy to overcome. So why would this be the case then? If it's London forces we're talking about, what affects the strength of the London forces? Well, it's the number of electrons, isn't it? We said the more electrons you've got, the more unevenly they can be distributed, the stronger London force you've got. Okay. The reason why this is higher than ammonia, which we perhaps wouldn't expect, is just because bromine has so many more electrons than there are in the NH3 molecule. Okay. That even though London forces are a very weak force, with that many electrons, it actually ends up being stronger than the hydrogen bonds. Okay. So I think we want to explain that. This is because bromine has many more electrons than the other molecules, than, well, let's just say than NH3 and F2. So its London forces are relatively strong. Okay, and then the other thing we need to explain is why is the ammonia higher than the fluorine. Okay, so we can say NH3 has a higher boiling point than fluorine because hydrogen bonds are stronger than London forces. And then we could just say, like, in most cases, because that's clearly not the case compared to the bromine. So that is a bit of an unusual one, and I wanted to show that question deliberately, just to try and make the point that we learn this theory that London forces are the strongest, then permanent dipoles, then... Sorry, I just said that wrong, haven't I? We learn the theory that hydrogen bonds are the strongest, then permanent dipoles, and London forces are the weakest intermolecular force. But it's not quite as simple as that, right? And that is something we see quite a lot in chemistry, that, yeah, most of the time this is how it works, but there is usually an exception to the rule somewhere, okay? Another point that we can take away from this question is, if they've given you data, you need to explain what the data is showing to you, even if that goes against what you might otherwise think. If, this clearly, well, if that is the highest boiling point, it must be the strongest force. That's not what I would have expected, but that must be the case. So always go with the data that they've given you.